I've got this DC motor that I want to drive with my Arduino Uno. The problem is the Arduino specs say that it's not powerful enough to turn the motor off and on. How can I make this work? We'll find out today on this episode of The system that I would like to set up would be simply to have an Arduino Uno that would drive a DC motor and turn it on whenever I push the push button and turn it off whenever I release the push button. Pretty simple and straightforward, but we have to look at the requirements of all of these devices to see if it's going to work. So our first iteration or thought of a design would be to take the 12-volt motor, connect it directly to an output pin, pin 2 for example, on the Arduino, and have it directly drive the motor. Well, we've got some issues there. First off is the motor is 12 volts, so that when it is turned off, there will be 12 volts applied to pin 2 on the Arduino. The Arduinos will handle a maximum of 5 volts. Anything above that on any of the pins will damage the Arduino. So putting 12 volts on pin 2 will damage that output port and it'll make it useless for us from there on out. So that's the first thing. The second thing is that this motor requires somewhere between 100 and 130 or a few milliamps more in order to properly run it. Now, our specs for the Arduino limit the output for each output pin as either sourcing or sinking 40 milliamps per pin. So if we want to drive this motor, we would have to make the output pin 2 go low, and we would have to be able to sink 100 to 130 milliamps in that port that can only handle 40 milliamps. So we have a second problem there. A third problem that may not be so obvious is that when we turn this motor off, there is a significant amount of energy that is stored in the magnetic field that when it collapses, since we don't have current flowing through it anymore, it will produce a very high negative voltage pulse in order to dissipate the energy that will damage the Arduino Uno again. So we basically have 3 issues that we have to deal with in this design. The design problems are the motor voltage is too high for the Arduino to handle. It's 12 volts we need for the motor, 5 volts maximum on the Arduino. The motor current is too much for the Arduino to sync. It's way above 40 milliamps. It's about 2.5 times above the 40 milliamps. And this inductive kick will damage the output pin. So we'll look at another design iteration where we can start to protect the motor or the Arduino from the motor voltage and current requirements. And this is pretty straightforward. What we can do is insert a 2N3904 transistor in the motor circuit to handle the voltage required for the motor as well as the current flowing through it, the 100 to 130 milliamps. It will also allow us to isolate that from the Arduino Uno because the base of it will be driven through a resistor that will limit the current and the voltage that is required for driving the transistor. The other thing we've done is added a snubbing diode, they call it a snubber, that will automatically short out the negative voltage kick from the motor and protect both the transistor and the Arduino from that transient voltage kick. Now, the 2N3904 transistor specifications are down here. It has a 40 volt maximum from collector to emitter. We're only putting 12 volts on it, so that checks. That makes that compatible. The maximum collector current that it can withstand is 200 milliamps, which is above the 100 to 130 that we would need. And it has a gain of 30. The gain is going to help us connect it to the Arduino output pin. So we have everything we need, except we need the value for this base resistor, R sub B. So we have to calculate that. So how do we calculate this value? Well, I've isolated just the parts that we need to calculate here. We've got a current flowing through the circuit of 100 milliamps. All right, the 2N3904 has some other characteristics. It's got a gain of 30. We know that from before. That's called HFE. And it's also analogous to beta. You probably have seen beta as the same thing. It's a current gain in the transistor. Okay? And we've got the resistor here, and I've put the minimum output voltage for the Arduino output port there, 4.2 volts. All right. And the other characteristic we know is that there is a voltage potential we have to overcome in order to make this base emitter conduct, and it is 0.7 volts. Okay, so we need to find RB. Well, we can't find RB directly. We have to find one thing first before we find RB, and that is I sub B. What is the base current that is needed to turn the transistor on enough to sink 100 milliamps? Well, there is a relationship for transistors that says that the base current is related to the collector current by a constant of proportionality or gain called HFE. So I sub C is equal to HFE times I sub B. So we can calculate I sub B now. I sub B is basically equal to, if we solve this equation up here for I sub B, it's I sub C divided by HFE. Okay? We know I sub C, that's given. It's 100 milliamps. So that's 100 times 10 to the minus 3. And HFE, we got that from the spec sheet, and that is 30. So if we perform this division, we get the base current is equal to 3.33 times 10 to the minus 3 amps. Okay, so it's 3.33 milliamps. So if we inject 3.33 milliamps into the base, then it will allow, or it will create the conditions so that we can sink 100 milliamps from collector to emitter. So that's half the problem. Now, to find R sub B, we can use Ohm's law, and we know that if we have a resistor, we can find its value if we know the voltage across it and the current through it. That's basic Ohm's law. So if I have Ohm's law, which is E equals IR, I times R, then I can solve that for R, which is the voltage across the resistor, E across the resistor, and that's divided by the current I. Okay? So, that's Ohm's law. So R sub B is going to be equal to the voltage across it. Now, what is that voltage? Well, between here and ground, we've got 4.2 volts. But there's also a voltage drop between here and here of 0.7 volts. So what is the voltage across the resistor? It's really this 4.2 volts minus the 0.7 volts. So if I take 4.2 volts and I subtract 0.7, and then I divide that by the current through it, which we just solved, it's I sub B, and it's 3.33 milliamps right here. It's that value. We divide this by 3.33 times 10 to the minus 3. We get 1,050 ohms as being required to give us the 3.33 milliamps into the base that will then have the transistor conduct 100 milliamps from the collector to emitter. 1,050 ohms, though, is not a standard value. So we have to pick a standard value, which we can do very easily, but we have to realize one thing, that we want to have a minimum of 3.33 milliamps into the base to get that current. So we will select a lower value of resistance so that it'll conduct a little bit more current to make sure we get the response that we want. So if we select R sub B as being the next lower standard value of resistance, we will make it 1,000 ohms. All right, that's a 1K ohm resistor, brown, black, red, that we can put into the circuit. So if we go back to our original circuit here and we make R sub B 1K ohm, then the device should turn on and we should be able to reliably drive the motor with the transistor. So let's try it and see what it's doing. Here is the circuit that we designed. I've implemented it here. Here's our Arduino, of course. Pin 2 is over here. That's the output pin. Pin A0 is the input pin. I've implemented my push button here with just a regular push button on port A0. I did not worry about doing any kind of bounce detection or anything. And I've enabled the pull-up resistor inside the Arduino to make this push button work. So that's our input. Then we've got the transistor over here. Above it, you'll see that we've got the snubbing diode. It's kind of covered up with these wires, but you can see that right there. And here is our motor. Now, what I've done is I've wired a multimeter in series with the motor to measure the current that is running through the motor as we drive the motor with the Arduino. So all I should need to do would be to push the button and the motor should start. If I let up on the button, the motor should stop. Now, just to prove that the snubber diode has done its job, we can make the motor drive again and then turn it off. Okay, so this is one implementation of an interface between an Arduino and a higher current, higher voltage device that we want to drive, but it's not necessarily the best implementation of it. This will work. It's quick, it's dirty, it's cheap because these two N3904 transistors will run you just a few cents and you probably have them around anyway. And if you don't have a 3904, you can use a 2N2222. But it does have a couple of issues that we need to consider. Number one is that this transistor, 200 milliamps is the maximum current. We're drawing somewhere between 100 and 130 or 140 milliamps now. So we do not have a significant amount of overhead available for us to have a safety in case we need to change the motor that will pull a little bit more current, or if there's some other issues. So we're pretty close to the design limits on this 2N3904. The other thing is that there is a significant voltage drop across the 2N3904 transistor, which means that we will be dissipating power in the transistor. So power can be an issue in your devices, especially if they're battery driven. So we need to make sure that we keep that under control. So there's other ways of driving this motor. We can use relays, or we can use field effect transistors. And in one of our next videos, we will use the field effect transistor to drive this motor. So now you can go and you build your robotics. They can be reliable, and you can use your Arduino and have a good time. So until next time,